Okay, so this video is going to be all about acceleration and what uniform acceleration is. So what we're going to look at is the definition and then a few problems that are related to it. So right from the beginning on your sheet, you can see that acceleration is the speeding up, the slowing down, or the change in direction of an object. And that last one's actually very important to understand, this change in direction. And so I wrote here as well that acceleration is measured as the change in speed in a given amount of time. By definition, uniform, or what we call constant acceleration, is acceleration that's not changing. So it means that the velocity is changing, which is the speed with direction, but it's changing at a very constant rate. And the rate at which it's changing is not changing. That's something else. Now, I wrote here it's the change in speed. But in a lot of ways, what we can say is it's actually the change in velocity, since we're really dealing with directionality as well. So over top of our equation, sometimes we get lazy and we leave off the vector signs to show the acceleration, but they should be there, and that will help you to understand that an object can still be accelerating even if it doesn't change its speed, meaning it doesn't speed up or slow down. Simply, if it's moving at a constant speed but changes direction, that can only occur if a net force is acting on it, meaning that it had to accelerate. And if you can understand that nuance to it, then that's really, really important. That's a good thing. So now, the equation for it is very simple. You can see it here. Its acceleration is the change in speed. So this term here represents the change in velocity, okay? And because it has directionality, and which is typically, this could be meters per second, it could be kilometers per hour, it could be kilometers per minute, it could be any unit that's distance over time. In the bottom, we've got the change in time, or the time interval, and that can be in seconds, minutes, hours, years, whatever the case may be. Nanoseconds, doesn't matter. Days, anything. And what that means is that the acceleration, which has the symbol A, has both direction and magnitude. So it's a size and a direction. And the units for this, as I wrote below, could be all kinds of things. So this is the acceleration. I think that's obvious at this point. And it is both magnitude and direction. Now, the direction is defined by what the change in the velocity is, so the vector symbol of that. Acceleration can have lots of units. It can have units of meters per second, kilometers per hour per second, meters per hour per second, kilometers per hour per day, meters per minute per day, meters per day per minute. It doesn't matter. The key is that in it, right here, and I'll highlight this, the first point here, this one here, that is your delta V. That's how much the velocity is changing by. And the second part is the delta T. So it's the change in velocity per second. So this one here says that the object is changing a certain number of kilometers per hour every second. So that could be like a car accelerating. It changes at 10 kilometers per hour per second. Here it's meters per hour. That's pretty slow. I mean, if you have if you travel 1 meter per hour, that's not very fast. But if you speed up by 1 meter per hour every second, then after, in 1 second you're going 1 meter per hour, then you're going 2 meters per hour, 3, 4, 5, 6, and you're speeding up or accelerating. Now remember that an object that's slowing down is also accelerating. It's a negative, or perhaps a negative acceleration in that sense. All right, how can we figure out the value of delta V? Well, delta V, vector, and again, sometimes we just get lazy and leave the vector symbol off.
Please report to your period 4 classes. Thank you.
And that's awesome. Let me interrupt the video. And so when you have this delta V vector right here, it's V2 vector subtract V1 vector. So even if these two speeds were the same, you would think that your change in velocity would be 0. However, this could be going north, this could be going east, and therefore the acceleration, although it comes out as 0 if it was a scalar quantity, we find out that it would still be accelerating, it's just changing its direction. So it would still have acceleration. You would have to draw the vector diagram, figure out the displacement, and figure out the delta V from that point. So that's important, especially for later on in physics. For this year, we can be a little bit lazy with the vector symbols because we're just going to be talking about objects that are speeding up or slowing down in a one-dimensional sense. We're not going to worry so much at this point about two-dimensional directionality. So again, to find the change in speed, or the change in velocity, we take the final velocity and subtract it from the initial velocity. Okay, and again, for the most part, these will just be positive and negative, and so because we're going to be talking about one-dimensional motion. All right, so we've got that, the key ideas, and now let's take a look at the back here and see if we can answer a couple basic questions about this. So let's take, for instance, a situation where we have an object that's moving at 15 kilometers per hour per second, meaning that it's increasing its speed by 15 kilometers an hour every second that goes by. Please read that sentence over and listen carefully to it to make sure you understand what the 15 kilometers per hour per second represents. Now it says here, if this object started at rest, which was not moving, and in 2 seconds the object is traveling at 30 kilometers per hour. That makes sense. If you look at it, we say, okay, in the first, in 1 second, the object is going, so it starts at 0 seconds, the object's not moving. At 1 second, it's moving at 15 kilometers per hour. At 2 seconds, it's moving at 30 kilometers per hour. At 3 seconds, it's going to be going 45 kilometers per hour. And it's going to be increasing each time by the 15 kilometers per hour because it's doing that every second that goes by. Another way of looking at this is to say, well, you could rearrange the formula on the front, and I'm going to leave the vector signs out at this point just to make it, whatever, I've included them now. And if you simply multiply, it becomes a delta t is delta v, and the acceleration was 15 kilometers per hour. And if you put the time interval of 1 second, then it tells us our change in speed for each interval of time is 15 kilometers per hour, which we already kind of figured that out. We see that it's going up by 15 each time. And so the change in speed, or the change in velocity in this case, would be 15 kilometers per hour. And we don't have the unit of time because we're just saying that it's every second that goes by. All right, let's try another example here, example 2. And what we've got is, we know the acceleration of the object is negative 56 meters per second, and it means the object's slowing down by 56 meters per second every second. Let's say that we started out at 500 meters per second. How fast would it be moving after a time interval of 4 seconds? Now there's a couple ways of doing this. You could do it a sort of intuitive way and simply say, well, if we start at 500 meters per second, and every second that goes by, we're going to reduce it by 56 meters per second. And we're going to do that so this is our V1, and we're going to do this for each time interval, so 1, 2, 3, and 4 seconds. Then what we end up with is simply (276 meters per second. So at 4 seconds. So at 4 seconds, we would be down to a speed of 276 meters per second. What's another way of doing this? Well, some of you like just, the formulas and things like that, and so let's take a look at it. We had this formula, and we had this formula. Okay? So another way of thinking about this formula is just putting it together and writing it simply as as that. And you're like, okay, all you did is substituted in the delta V. Put a bracket around that just to make it easier. And now it says, we know that V1 is 500 meters per second, and we know the acceleration is negative 56 meters per second per second. So we have those two bits of information. So we know, I'll highlight the things we know. We know this, we know this, and we know V1. And again, of course, the time was 4 seconds. Okay, so we're good. What we can do is we can isolate for V2. Multiply the delta T up. I'm just going to remove the brackets at this point because it's one term. Now I know V1, so I can bring it over. It becomes V1. So you have to add it to this side. And there we go. Now, sometimes when we do it, we like to write it this way. Like that. All right, so that's good. This is actually what we'll find out is one of our kinematics equations. In fact, it's the second one. And if we plug in our values for this, you will quickly see that if we put 500 meters per second plus negative 56, I'll leave the units out for that one for now, and the time is 4, just because I was going to run out of space, you would find that you would get the here A delta T. If you're really thinking about this A delta T is our change in speed. So we would say, well, it was moving at 500 meters per second, and it changed its speed by 56 times 4, which is, it changed its speed by 224 meters per second. That's how much it changed its speed. And the result is 276 meters per second is the final speed. Same answer that we got before. Okay. So now what we're going to look at is some problems related to this. I'm going to leave them for you to do. It says they're examples, but you will be able to do them based on what we've just done through this lesson. So I will put that up here. And so what it looks like is this here. There we go. So write the acceleration equation and the two other variations. So the one that we had was that acceleration is delta V over delta T. Okay, that was the basic starting equation. We also know that really delta V was V2 minus V1 over delta T. That's a key equation. And then from the previous one, we multiplied delta T, added V1, and we found that V2 was V1 plus a delta T. Now, there are different rearrangements. From here, you can basically solve most of the problems that we need to find by simply saying, you know, if you were looking for V1, but you knew V2, you know acceleration, and you know the time, you would have to move the A delta T over to isolate for V1 by subtracting it. So it's some very basic mathematics to get from those points. So you can really, with this equation and this equation here, this one's exactly the same equation, then you are able to solve all these acceleration problems at this point. So, you know, for instance, here's one here where it says there's a clown car moving at 12 kilometers per hour and accelerates at 1.3 kilometers per hour every second, reaching a speed of 27 kilometers an hour. Calculate the time required for this change in speed. So we know our V1. We know this is acceleration because it's distance, time. Distance per time per time. And that automatically tells us that's an acceleration, reaching a speed of V2. So we know V1 is 12 kilometers per hour. We know that V2 is 27 kilometers per hour. And we know the acceleration is 1.3 kilometers per hour per second. So it says, how much time would this take? So you could start counting by 1 second intervals, because this is per second, and you could say, oh, okay, well, if it's going up by 1.3 every second, you go 12, so 13.3, 14.6, 15.9, and go all the way till you get to 27, and just count how many times you did that, and that will give you a rough estimate of the time. Or what you can do is you can use this equation, which is just a rearrangement of the acceleration equation, and isolate for time. You'll see it's just simply subtract v1, and then now we've got these two things multiplied, so the time would be v2 minus v1 over a. You plug in your values. Remember to do it with brackets. Really important at this point to make sure you always put brackets, and you will get your final solution, and your answer will be in seconds because it's kilometers per hour per second. It's important to realize the brackets up here when you're substituting in your values, and also make sure that you get the value at the top first before you divide it. Some calculators require brackets to do that, some it doesn't matter. See if you can finish up the rest of the problems on this sheet from this point. Thanks.